All right, so thank you for being here at the last talk, and thank you to the organizers for inviting me. It's a great honor for me to be here at the conference in memory of Jean-Christophe Yoccoz. I was very happy when I was invited because I was very happy also to share this celebration, and since he was a great mathematician, but also he was a great person, and I liked him very much as a person, and he was very influential for me, for my research from the very beginning. In fact, I don't quite remember the first time I met Jean-Christophe. I think the first time I saw him, he was often with Michel Herman, and I was kind of very intimidated by maybe the couple. But I do remember the first time I read his papers, some of his papers, and one of them played an important role in one of my first works. So I'm going to tell you a little bit of this, and then I'm not going to focus immediately on my topic today, but I'll just begin by reviewing this, memory of the impact of Jean-Christophe research on my first steps as a researcher. So, well, what I want to talk today is the general theme can be summarized in the sentence that it is useful to solve cohomological equations, so maybe I don't have to convince many of you, but the cohomological equation is either this linear partial differential equation, xu equal to f, so we want to solve, given f, we want to solve for u, and it could be for a map, but I will mostly stick to flows, although, of course, both are important. And the questions, very generally, that I'm curious about is that, and I'm playing with, is what we do it for and how. And I'm going to focus on systems which have no hyperbolicity, so I'm not going to talk about Lipschitz theory or the partial hyperbolic case, and I put some names of people that contributed there. This doesn't have to be, it's not necessarily exhaustive. And so why I got to cohomological equation? Well, my initial motivation was stability. Well, linearized stability doesn't make much sense as a sentence, but I meant to the stability for the conjugacy problem. So if you have a conjugacy problem and you linearize the conjugacy problem, then you can get to cohomological equation and try to apply the KM method. That was the first motivation, and then later there was also motivation coming from understanding deviation over ergodic averages that was prompted by Zorich. Oops. What did I do? So I have to be careful not to touch this. So it was prompted by Zorich's work, and in some sense the point is that, of course, if we can solve the cohomological equation, then you have Goschak-Edlund, or simply just fundamental theorem of calculus tells you something about ergodic integrals, and also the other motivation are ergodic theory of time changes. So these are some of the themes that I pursued. And the how is, well, in most cases in my work, I've been using Fourier analysis, and in particular representation theory, but another way would be to try to use renormalization. And I will say something more about this in connection with Jean-Christophe's work. And so, well, this is just to, order zero of the cohomological equation is the case of the torus. So in the case of the torus, if we look at a linear vector field, you want to solve the cohomological equation, we can do it by Fourier series, as everybody knows, and that's more or less the formula that we get by solving by Fourier series. The formula makes sense when the F0 coefficient is 0, which means that we have only a single abstraction to solution, which is the average, and we see small divisors appearing, which are this scalar product of the frequencies with integers, and another. So then we have to assume the Diophantine condition that I haven't written. And under the Diophantine condition, we'll have some finite loss of derivatives. And so my motivation at first was I wanted to generalize this to other systems that are again, not hyperbolic. So the generalization here I'm going to mention, of course, translation flows. That it was the paper I'm going to tell you a bit more about. And then the work of Marmi and Yoccoz. There should be not a comma, but this is, of course, 3-author paper in 2005. Then, in collaboration with Livio Flaminio, we studied the case of Horocycle flows on hyperbolic surfaces in constant curvature, and the case of nil flows. And then, more recently, also I want to mention the work of Giulietti and Livarani for flows along foliations of anodes of maps of the two torus. So these are some directions of generalization. So there is a lot here, but let me try to. So that's up there is more or less the statement of what happens for the translation flow case. So let me just maybe use the chalk to put down a couple of things. So the point is that the statement I put for the D torus, of course, holds in particular for the two torus, and the idea is was to try to generalize to higher genus surface. So this would be a case of a genus 2 surface, and on this genus 2 surface there should be a translation structure, which means that essentially I want to have two vector fields, say the horizontal vector field and the vertical vector field, and these two vector fields behave like more or less like two vector fields on the torus, except for the fact that, of course, topology prevents the two vector fields from commuting everywhere, and we'll have to have singularities. So the singularities, you may imagine that the two orbit flows behave like saddles. So that's a caricature of a translation surface in genus 2 with two singular points. The picture of the singular point represents the orbit structure of one of them, not the other one. So if I try to draw both of them, it will become a bit messy. So this is the idea. So how to do that? So how to go from the case of the torus to the case of a higher genus? And the key idea came from essentially reading or going around Jean-Christophe work, and the main idea is that one should try to complexify the problem and then approach it by taking boundary limits or radial limits of solutions. So once that point of view was, once I took that point of view, that it was somewhat simple to proceed, because then, okay, we have x and y. What I wrote there is a translation frame, so two vector fields which locally behave like ddx and ddy. Then the idea is that to introduce a parameter, the angle, and try to solve for the typical angle. And the complexified system is naturally given by a Cauchy-Riemann operator. So what happens if you complexify a vector field? You get a Cauchy-Riemann operator. So one can write the vector field x theta in terms of so maybe I should use the pointer, but I'm not very good with these things, so maybe I will change page. But anyway, so maybe you don't need that. So writing the vector field in terms of the Cauchy-Riemann operators, and then essentially what one sees is that there is this operator x plus iy, x minus iy minus 1. So it's the composition of a Cauchy-Riemann operator with the inverse of its complex conjugate. And that is essentially a unitary operator, is U down there. And I discovered many years later that should be called a Bjorn transform, but I didn't know then. And essentially the problem becomes trying, if you want to invert the vector field x theta, then the problem becomes to invert, to solve, to find the resolvent of the unitary operator at the unit circle. And of course, one cannot do that because the unitary operator will have spectrum on the unit circle. So the idea is to take Z inside the unit disk and then try to work with taking radial limits, like Jean-Christophe did in the, I don't know why he does this. Right, password? Okay. Huh? I have to access? Yeah, but I don't know. Yeah, I know you will do it again. Yeah, but I don't know to do it. So sorry. So I will. Yeah, that's sorry. Yeah. So that's the idea of the proof, and then from there, essentially, the point is that the resultant unitary operator is given by Cauchy integrals, and one gets Cauchy integrals of measures, and there is a well-established theory in harmonic analysis for how to study Cauchy integrals of measure and how to estimate boundary limits, radial limits at the boundary of the unit circle, of the unit disk, of Cauchy integrals of measures. So that's essentially the basic idea, and it came from the idea from Jean-Christophe's proof that was published in 1995 of a Siegel-center problem for almost all rotation numbers by essentially a similar idea. So I took it from him, this inspiration. So this is how you solve the cohomological equation in a higher genus case. If you ask where the abstractions are coming from, I'm not going to, I mean, that's the start of the proof. It's just to say that the main idea of the proof, so how do you do harmonic analysis on translation surfaces, trying to generalize the case of the torus? Well, you complexify the problem, you consider Cauchy-Riemann operators, and then you try to take radial limits at the boundary of the unit circle. That's the essential idea. And you see that what appears is this Bernoulli transform, this unitary operator that for which the invariant measure, the spectral measures are the relevant objects.
No, but I mean this inversion.
Yes.
It's an inversion. Conjugate something to something, or what?
No, if you want to solve the cohomological equation x theta u equal to f, it's like inverting the operator x theta, right? So it's essentially what you want to find is x theta minus the inverse of the derivative operator. Of course, this is a kind of a rough account. There is a Cauchy-Riemann operator still in the picture, and so on, and one cannot invert in the L2 space. There are many technicalities, but this is essentially the key idea. So later, Marmi, Musa, and Yoccoz in 2005 gave a new proof, and in fact they took the point of view of intersense transformations. So I want to mention just a few things about this proof. So first of all, so there are many advantages of this proof. Some are really crucial for later developments. So first of all, they have an explicit Diophantine condition that Corina Ucegrai mentioned yesterday, a Roth type condition that in my case it was just almost all angles. It was purely full measure statement, but no condition. They have a smaller loss of regularity. If I'm not wrong, it's 1 plus bounded variation, but Stefano can correct me. And I had 3 plus at best. And when I say 3 plus at best, it came after working hard. Jean-Christophe asked me, what is the best you can do? And I really worked hard to show him that I could do 3 plus. And of course, 3 plus was not enough for the next step. So and for me also important is that until recently, this was the only, as far as I know, solution of a non-hyperbolic cohomological equation by a dynamical method. So I think the first solution of a cohomological equation for a parabolic system by Fourier analysis, I mean, I'm not talking about the torus. So showing parabolic features was by Katok. Katok did the case of the skew shift, so skew shift on the torus, right? Linear skew shift on the torus. But all examples stayed of algebraic nature, and the proof stay of algebraic nature, harmonic analysis based, until this paper where they were able to do it by renormalization approach. And so, of course, this one can ask how to generalize this kind of dynamical approach. And recently, there's been a paper by Giulietta and Livarani that can get essentially generalization of the dynamical approach by analyzing the transfer operator of the renormalization dynamics, that in their case is an Anosov map over 2 torus. So naturally, one would like to generalize this further to Horocycle flows, and I know that there is work in progress by Alexander Adam, and then nil flows and maybe other examples. So the dynamical approach should be more powerful, more flexible than the one based on representation theory, that the one I know best. So let me just go one step back and just, I want to tell you about motivation. Why did I get to this problem? Well, the question I started with was the following, and so it's a little bit crazy, but why not? I want to mention it. So you can consider a rational polygonal billiards. This is the kind of system that were mentioned in Kerr-McMullen's talk. So if you take a billiard in a polygon, say this is an example, a simple example of a polygon. So you look at the billiard, and the phase space of this billiard is a genus 2 surface across an interval. So this is the phase space. And the phase space is foliated by genus 2 surfaces. And on these genus 2 surfaces, there are translation flows, linear flows. And of course, you might want to do the same that you do for the torus. So the question is, can one perturb on a finite codimension family a billiard like this without touching the corners in a way that some of these invariant surfaces persist? So of course, if you start with that, then you say, well, I mean, what do you do in the case of the torus? You do KEM theorem for the torus. The first thing you do is try to solve the conjugacy problem. So you see, I was very naive, so that was the warm-up. The warm-up was to to solve the smooth conjugacy problem. Now, obviously, I wasn't able to do it, and the reason is that the KM method runs into trouble because in the case of translation flows, there are lots of abstractions, and these abstractions have arbitrarily bad regularity. So the new phenomenon that appears for translation, for cohomological equations of translation flows is this abundance of very bad abstractions. So to this day, I think the KM approach is unknown, is not developed. So Marvin Yoccoz in 2012, I think, but maybe I have the wrong year, but around that time, well, that's the publication year probably, they were able to go by another strategy to prove this result that I've, one of my dreams, so the smooth conjugacy result. So basically, roughly, this says that if you want, you can perturb your linear system on a finite codimensional family and find a system which is smoothly conjugate to the original one. So it's a smooth conjugacy result, and the higher you want the higher the smoothness for the conjugacy you want, the higher the codimension. So you have to reduce your family, increase its codimension if you're asking for conjugacies which are of higher and higher regularity. So the proof, I put a few lines, is based on a somewhat special feature of this problem, that its interest transformation are piecewise linear, so one can use the Schwarzenberg derivative method first used by Arman in the circle case. And let me just say that I haven't given up on KEM. I think it's an important direction anyway, because, for instance, there are other systems that one might want to know about, and also in higher rank parabolic action case, there are similar situations where there may be a lot of abstractions that pop up, and it would be good to be able to go in that direction as well. So here I have a. I'm sorry for this. I don't know how to. Maybe one of you knows. Yeah. So where was I? Yes. So yeah. So KM theories. Okay. Yeah.
This is the result of Marvin Yoccoz. Is full measure nevertheless? Full measure?
Yeah. It's under. Yeah. Basically, it's under the rho type. Under.
Works for bounded type.
No. I mean, it's a rho type. It's rho type.
Yeah, they get full measure.
It's rho type. Yes, they get full measure, yes. I mean, yeah. So at some point, what I really got interested in is what one can do when there is no renormalization inside. So the problem is that there are some parabolic systems which are renormalizable, and in whatever that means, but there are many which are not renormalizable, and in particular, there are many unipotent flows that are not clearly renormalizable, and one would like to know, like to be able to study them. Now, the motivation here becomes really effective equidistribution, which means deviation over ergodic averages rather than conjugacy problems. And but before going there, let me maybe focus, introduce you the main actor. So the main actor now is going to be the Horocycle flow. So the Horocycle flow is given by the action of this subgroup of SL2R on a quotient of SL2R by some lattice gamma. So that is going to be my main actor. But what I want to study won't be like usual ergodic integrals for the Horocycle flow. Here I'm just recalling some property of the Horocycle flow. So it's been long studied as an important example of parabolic unipotent dynamics. So it's a minimal unique ergodic flow, and well, there are a list of properties. There is an interest from the point of view of number theory, since there is a connection that I mentioned a little later to the Riemann hypothesis in the non-compact case. So you can see that there are papers on the asymptotics of ergodic averages first by Zaghir and Sarnak and Eshal, and then many other works. Stromberg's on myself and Livio, Flaminio, and also with Sasha Buffetov. So all these papers are related to and study the fine deviation of ergodic integrals for the Horocycle flow. So obviously this is not not my focus for the non-renormalizable case. This is a renormalizable case, but let me just, for comparison, walk you through some of the results. So now, from now on, HT will denote the Horocycle flow, and GT will denote, or GS, actually I probably use GS to distinguish the two times, the geodesic flow, and this is the result, well, the final form of the result that started with a paper with Flaminio in 2003, and this is the version given with the paper with Buffetov in 2014. So there exist older functions, this B plus minus, on the phase space. So the phase space is the quotient of SL2R by gamma, so it's a three-dimensional manifold, and such that we get the asymptotic that is written there. So let me just make some comments about this asymptotic. Well, first of all, the parameter mu is related to the spectrum of the Laplace operator, so there is some input from analysis. And second, the coefficient d plus minus mu of f are values, the d plus minus mu are distributions, are linear functions or smooth functions. These distributions are invariant. I will say something more shortly about what that means. So, the function appears through these linear functions, d plus minus mu. And then there are these other functions, b plus minus mu, that are evaluated along the orbit of the geodesic flow at logarithmic times. So these functional b plus minus mu, they were first introduced by Buffetov in a paper that was mentioned yesterday by Corinne Alcegrai for the case of translation flows. So in this paper, in this joint paper, we sort of show that they actually generalize to Horocycle flows by the same kind of method. And they were essentially mentioned also again by Corinne yesterday, and when she talked about limit shapes. So essentially limit shape and Buffetov functions are one and the same. So these, you can say, are limit shapes for Horocycle flow. So it's essentially a dynamically uniquely defined, dynamically way of introducing coefficients and the main feature is that they appear like along the orbit of the geodesic flow, along the orbit of the renormalization dynamics. So that's the way that. The other comment I want to make is that the exponent, the powers that appear there, is t to a certain power. These powers depend on the spectrum of the Laplace-Beltrami. So you can see 1 plus minus square root of 1 minus 4 mu divided by 2, whatever that is. It's a number that depends on the. These are numbers that depend on the spectrum of the Laplace-Beltrami operator.
Is your spectrum positive?
The spectrum is positive here. Yeah.
So when mu is bigger than a quarter, those are just at the size t for 1/2?
Yeah, when mu, you're right, absolutely. There should be a real part. Yes, that's a misprint essentially. So that's important. It's irrelevant remark is that when mu is bigger than a quarter, of course, what you see there is it's a phase. Well, the phase is there. You can leave it if you want. It means the asymptotics is not just not just the size of the integral, but also it keeps track of how this oscillation behaves. So in the case of mu bigger than a quarter, there will be an imaginary part, and if you're only interested in the size of the integral, then you get a square root of time. Yeah. So, all right. So in particular, consequence of this asymptotics were results on limit distributions for the Horocycle flow. In particular, this Horocycle flow doesn't satisfy central limit theorem. This was already established in the joint paper with Flaminio. So all this goes back to a result by Sarnak, and before Sarnak, or simultaneously more or less by Zagier. They were studying the cuspidal Horocycle case, and the motivation. So in the non-compact case, the Horocycle flow has a one-parameter family of periodic orbits that are called cuspidal Horocycles. In that case, Sarnak gave an asymptotics, and as far as I know, this is one of the first places where these objects in variant distribution, this d mu, appeared in the literature. I'm not sure they appeared earlier than Sarnak's paper. So so there is a connection to the Riemann hypothesis. So I think that justifies the interest of a number of theorists in this kind of questions. So so this is very quickly. So in the above theorems, the invariant distributions are this d plus minus mu are solutions of this linear equation. So when you take a distributional derivative of d plus minus mu by the generator of the Horocycle flow, which I call u, you're supposed to get zeros. That's what that means. You use a test function f, and when you evaluate d plus minus mu on the Lie derivative of the test function, you're supposed to get 0. And our proof with Flaminio and also with Sasha Bufetov are really based on solving the cohomological equation first, and then using renormalization. In this case, renormalization is simply given by the geodesic flow to get to ergodic integrals. And solution of cohomological equations, as I said, is based on theory of unitary representation, so it's very much special for the algebraic case. So now the goal of today's talk really was, the focus was to go from the Horocycle flow to twisted Horocycle flow, or to twisted integrals for the Horocycle flow. So they are there. So H is still the Horocycle flow, but now I multiply times e to the I lambda t, and I integrate. And again, the goal is to understand how these integrals behave quantitatively. So try to find bounds for this. So in the literature, this type of integrals first studied, or at least the first bounds I know in the Horocycle case, were given by Venkatesh in a paper published in 2010. And the motivation, I believe, by Venkatesh was sparse equidistribution problems. So what does it mean, sparse equidistribution problems? Here is an example, Chaire question. Chaire question is the following. Suppose instead of taking Horocycle at continuous time, I take Horocycle not just at discrete times, but even at polynomial times. And n1 plus gamma is a sequence of polynomial time, where gamma is some real number, doesn't have to be an integer. Is it still true that as I average along a polynomial sequence, I get equidistribution? So this is yeah. Yeah, this is in the compact case. Yeah, I probably haven't written this, but I think the original question by Chaire is in the compact case. Another example of sparse equidistribution problem related to the Horocycle flow was considered by Sarnak and Sarnak-Ubis. And in that case, you sum over primes. So instead of a polynomial sequence, you have prime times, and you average over some final set of primes up to a certain threshold. And again, the question would be whether you get equidistribution. And I'm not going to touch that because that's a harder problem. And for some reason, maybe I'm not going to explain. Whatever we do doesn't get to the Horocycle flow at prime times. There are extra ingredients that we are not able to, so far, to get to. So, excuse me?
What value would you like to get?
Yes, so Chaire question is any gamma. So yes, so this is, you clearly see that we are in a very bad position here. So, and we are playing with very small improvements. And there is a conceptual barrier to do something serious about this, which is the following. The main idea behind this is to approximate the polynomial sequence by a sequence of arithmetic progressions. So basically, you look at your polynomial sequence, a chunk of this is going to be more or less like an arithmetic progression. And then this brings you to the time T-map for the Horocycle flow, and the time T-map for the Horocycle flow brings you to the twisted integral. So the chain of the logic from the Chaire question to the twisted ergodic integrals is exactly this, from polynomial sequence to arithmetic progression, which is time T-map for the Horocycle flow, from time T-map to twisted integrals. So let me just finish the comment. Of course, to get good approximation of a polynomial sequence by arithmetic progression, you need the second derivative to be going to 0, which means that this ideology cannot get beyond gamma less than or equal to 1, essentially, which is, of course, very far from say, the hope, so to speak. It's betraying me again, so. Oh, why that goes out? Okay, so yeah, so that's Chaire question. So let me just get to results. So these slides is a bit too full. More or less, this recalls that in the non-compact case there will be Diophantine conditions. So what are Diophantine conditions? Essentially, you want to know that under the geodesic flow, your point is not diverging in the cusp too fast. So there are several sets that specify what is the speed of divergence and maybe even the constant that I called for the statement MAQ, right? And I recall some property that if the union over Q of M1Q is the whole phase space, and the logarithmic law of geodesics is what is stated there, that the lim sup of the distance from a base point of the geodesic trajectory divided by the log is going to be equal to a half. So the moral of this is that we need some conditions that the points in the manifold, in this tree manifold, are not escaping too fast under the geodesic flow. And this is basically the Diophantine condition in this instance. Then we need some regularity for the functions. So there is a Sobolev space, WRM is the Sobolev space, some standard Sobolev space of square integrable functions with R weak derivatives. And with these notations, we have the following result that was appeared in GAFA and is by Livio Flaminio, myself, and James Tanis. And most of the work was done, in fact, when Tanis was postdoc at Collège de France, and was basically done not in this building, but not very far. So what is it saying? Well, as you can see, basically, this is a statement that says, under Diophantine condition, we have a quite precise estimate for the ergodic integral in terms of the phase lambda and the time, and you can see also the constant A appearing, which measures the speed of divergence of the point X under the geodesic flow. And there is a statement here also, what happens if we, for typical points, using the logarithmic law of geodesics. So what is the point of all this? Well, first of all, you see that the exponent, there is a signature exponent, 5, 6. These exponents get worse and worse as A goes to 1, which as it should, because as A goes to 1, the Diophantine condition gets weaker and weaker, and you don't expect it to have a result when it completely disappears. There is also some precise exponent on lambda, but I want to focus on the 5, 6. So if we compare with the Horocycle flow, one thing that we notice that 5, 6 is uniform. It doesn't depend on the spectrum of the Laplacian. So this is the first new fact. And the other thing is 5, 6 any good? So, well, we get to this 5, 6 with a proof that I don't know if I will have time to sketch, but anyway, the proof is a bit, there is no reason in the proof that we may think that this 5, 6 is a correct exponent. So we have an upper bound, but how good is it? So luckily, we could turn to analytic number theory to make a comparison, because this result, when specialized, well, we can specialize it to the compact case, but also specialize to cuspidal horocycles. So we specialize to the compact case, it looks much simpler, so it may be more appealing. But the point is that since we can do it also in a non-compact finite area case, finite volume case, we can treat the case of cuspidal horocycles with some restrictions on lambda. There is a relation between lambda and time. Lambda t has to be 2 pi z. Excuse me? Yeah, r bigger than 7. R bigger than 7 is presumably not optimal. Yeah. So if you can say it's technical in the sense that you need some regularity. You lose the regularity by solving the cohomological equation. Then you lose some regularity here and there. We haven't tried to optimize it. So it maybe could do a little better. Maybe not. I'm not sure.
And 7 is 6 plus 1, or the 6?
No, 7 has nothing to do with 6. It would probably be better to say, R large enough. So it doesn't really matter. I mean, it's like it comes about in a completely different way. But that's a specific threshold that we get. And so yeah, I'm more interested in this 5, 6, and well, the intuition in this problem is that. Is written here, right? As basically for small lambda, you have equidistribution of the Horocycle flow, and for large lambda, the phase gives you oscillation. And the fact that the spectral gap doesn't appear is related to the fact that there is additional cancellation given by the fact that there is an oscillating term, e to the I lambda t. So Venkatesh approach is very different from ours. It's based on the mixing of the Horocycle flow and on some ingenious mixing, and also equidistribution of the Horocycle flow, and some ingenious ad hoc ideas. And it has been also improved by Tanis and Vish that I also mentioned earlier. They improved by the same kind of method. They improved a bit Venkatesh results. In particular, they get this uniformity of the exponent on the spectral gap. So I wanted to discuss how good is this 5-6, right? And that was my main point right now. And it turns out that one can apply the result when considering the case of a Cusp Horocycle to get bounds for Fourier coefficients of Cusp forms. So not that I know much about Cusp forms, but this is the definition. So we have functions on the upper half plane that have a certain transformation under the action of elements of our lattice, or actually group, and they have an expansion. Since assuming that our group contains the transformation x into x plus 1, we can define Fourier coefficients, so they are given by that formula. And there is a well-developed literature about how fast this Fourier coefficient can grow with n. And there are two cases when the Cusp form is holomorphic and when the Cusp form is not holomorphic, which is called the mass case. And this is the result we get. So it's an, so corollary of our main theorem. We get a bound in the bound we can read there. So it's the absolute value of n to power k over 2. K is the weight of the Cusp form that appears in the transformation rule up there. Minus 1/6. This minus 1/6 is exactly coming from the 5 over 6. And we get some logarithmic term that we haven't bothered to really push whether you can get rid of or not. So it's there. So, and then we can compare to number theory result, and this is actually the best known result in number theory up to the logarithmic term in one case. So the best, as far as I know, and I'd be glad to be corrected because I'm very curious about what maybe recent progress on this problem. In the holomorphic case, the best result for general gamma is the result by Good in 1981 that proves this result without the logarithmic term. So it's exactly the same, but just not without logarithmic term. And in the mass case, there is a paper, almost 20 years later by Bernstein and Reznikov that actually do slightly worse than us because we have a log and they have a little power, arbitrary little power. They also have 1 over 6? Yeah. They do have 1 over 6. So this is a cohomological equation proof of this, essentially, of this result from analytic number theory. Now, for congruence, to be completely fair, this may just mean that these results are not so deep as far as number theory goes, right? Because if we can get them, right, with representation theory. So the deep stuff is, really deep stuff, is for congruence lattices. Then the Ramanujan-Peterson conjecture that were proved by Deligne, or at least consequence of the work of Deligne, state that you can actually get a half instead of a 6. Now we cannot touch that. I have no idea how you go there. So these results are for any gamma, so for any subgroup. So if you go to congruence lattices, then in the holomorphic case, you have the Ramanujan-Peterson conjecture. As far as I know, in the non-holomorphic mass case, the Ramanujan-Peterson conjecture is open. So, and as far as I know, nobody knows whether these results by Good and Bernstein-Reznikov are optimal for general gamma or not. So I think if anybody has any idea about that, I'm very curious. Or maybe I'm not doing it right. Okay, we'll come back to life probably, but yeah. So, okay, so how much time do I have? So, not much. Maybe 5 minutes, 10 minutes? 10 minutes, a lot of time. Okay, so let me just say a few things about the method of proof. The method of proof, first of all, is to treat the twisted integrals are standard ergodic integral of a twisted flow. So the twisted flow, and this in some sense is also related to the fact that we hope to be able to maybe generalize this to other unipotent flows or who knows.
So essentially unipotent flows. So our flow is going to be a flow on the parallel of M cross the circle. And this flow is just a linear combination of, sum of the Horocycle flow plus the generator of a linear flow on the circle. So theta is just dd theta. The generator is just derivative. So, and the point is that this flow is not renormalizable. I mean, there is no dynamical system that scales this flow, right? So the geodesic flow doesn't scale this u plus lambda theta. So what to do? Well, the basic philosophy here is that, well, what is renormalization? Renormalization is essentially change of scale plus change of coordinates. So rescaling followed by change of coordinates. So the rescaling makes your long orbit, excuse me? And renaming, okay. Well, change of, yeah, and renaming, but yeah. Okay, so the way I view it, the main ingredients are you change scale, essentially what you do, you change scale in a way that you change the metric, and your long orbit now looks short in the new metric. But now once you have a new metric, you also want to change coordinates to make your manifold look like nice, thick, recover a bounded geometry, basically. So what we do here is that, okay, we don't change coordinate, we just rescale. So we don't know how to change coordinate, we don't have a dynamical system acting on the space of all systems, we just do a scaling. Notice that this scaling is not very natural. Doesn't come from anything homogeneous that I can see. There is nothing in the Lie group that suggests this scaling. This scaling came to us basically by looking at this, how the invariant distribution, the abstractions for this cosmological equation, how they scale under scaling. So we price scalings, we looked at the corresponding scaling of the abstractions. The norm of the abstraction scales when you scale the norms, and we optimize this scaling. So if you try to optimize the behavior of the scaling of the abstractions under the scaling of the metric, then you get to this minus a third, minus 2/3. And so basically, the idea is that we just change the structure, the Riemannian structure on the manifold, and we consider adapted Sobolev norms, and we do estimates using this scaled Sobolev norms. And main point is the above scaling is not given by any dynamical system, which, I mean, of course, you can always think this is a dynamical system, but there is no recurrence, so it's hopelessly dissipative, so everything goes to infinity. But the point is that, if you want, the point in some sense is that it doesn't matter if there is no recurrence, what matters is bounded geometry. So you don't want the geometry to escape, to blow up too fast. So if you have a bound on how fast the geometry degenerates, then you can still get some results. So for a comparison, this is the scaling given by the Horocycle flow in the by the geodesic flow in the Horocycle flow case. So if you let the geodesic flow act on U is the one Horocycle, X is the geodesics, and V is the other Horocycle, so these are generators. The Horocycle flow acts by scaling U and V by e to the S and e to the minus SA and leaving X invariant. So that's a scaling that, of course, we use to study the Horocycle flow, but that one is given by a change of coordinate. This change of coordinate is nothing but the geodesic flow itself. So, and another remark is that the effective equidistribution of the Horocycle flow is a manifestation of the exponential decay of correlation for the geodesic flow. So the usual pattern is that the equidistribution of the unstable is nothing but some sort of refined exponential, some sort of refined decay of correlation, or in this case, exponential decay of correlation for the renormalization dynamics. All this we lose because the renormalization dynamics is not there anymore, essentially. So that's the price we have to pay. So the motivation, again, is the fact that there are many non-renormalizable situations, including higher step-near flows and non-rational polygonal Billiard flows, and it's not clear what to do in these cases. So what we try to do is some kind of this scaling without change of coordinates approach. So now, that's just to, I don't have much time to explain the rest, but let me just add one element. So when maybe I'll just do a little picture. So when we do normalization, essentially what happens is that we have say, a very long orbit. So we take a very long orbit, and the very long orbit comes back. So this is supposed to be an horizontal orbit, and then we have some change of coordinate, and in this change of coordinate, the orbit looks like of length 1. So maybe just something like this. Just a random picture. So you have, so this is the scaling. Here we do a scaling on this picture, and then a change of coordinate. And we get to a length 1 orbit. Now, the length 1 orbit, it can be put in a box, and basically this box is of size 1. So this means that in a renormalizable situation, there is a box, injective box, roughly of size, 1 over t. So 1 over t would be in the transverse direction, and t will be in the time direction. So, and this is important in the estimates, that the fact that renormalization gives you boxes which have controlled size in the time direction and in the transverse direction. So this we lose when we scale in this strange way. We lose this property that we have boxes in the new coordinates which are of this nice, which are rectangular boxes with sort of constant size. So the main technical ingredient, besides theory of representations and analysis, is the idea that we don't need the box to be uniformly thick. It's enough that the box is thick in average. So the box, sometimes the tube around an orbit will have to shrink to keep being injective. But the important point is that it doesn't shrink too much too often, and that there is a quantity that we call the average width, which basically says that if we look at an injective tube around an orbit, and you measure the area of the cross-section, and you integrate the 1 over the area of the cross-section, this is finite, it's bounded, it's under control. So it's some sort of an average, the returns are not too close in average. So that's essentially what this means. And it is done with respect to this scaling that I mentioned earlier. So basically, this is just a statement of the fact that we can control, the main point is that we can control this average width in this case. And the last word is that how hard is this? Well, this is very easy, in fact, in this case, because the divergence of orbits of this flow, the twisted Horocycle flow, is linear. So whenever the orbits have linear divergence, we don't see a big problem. But in general, the orbits may be more sticky, so they may have quadratic of higher order, not contact, but point of closeness. And they may stay close for longer times. And if the divergence is not linear, then this method runs into serious problems. And these estimates are not at all easy to carry out. So this is all I wanted to say, so thank you very much for your attention.